Okay, ladies and gentlemen, here we are with a 50 kilogram steel file cabinet that is in the back of a dump truck. The truck's bed, also made of steel, is slowly tilted. What is the magnitude of the static friction force on the cabinet when the bed is tilted 20 degrees? And at what angle will the cabinet begin to slide? Well, let's start off with that first question, obviously. We've got the bed is at about 20-degree angle here. Got our file cabinet on the bed, which this is either a giant file cabinet or a very small dump truck. Okay, and we just want to know, okay, so first off, let's start with the forces acting on it. Well, we know we've got the weight of the object straight downwards. We know we've got the normal force of the object at a 20-degree angle from the vertical. And then we've also got a force of friction. All right. So, very nice force diagram, but not so useful as a free body diagram. So let's draw the free body diagram, where we've got our file cabinet, like so. Got the weight of that file cabinet. We know that the normal force should look something like that. And the normal force and the force of friction are perpendicular to one another. So this is what our free body diagram should look like roughly. Now, I'm going to mess up this free body diagram by putting a coordinate axis in there. Going to make that x. I'm going to make this y here. Now, that works out well because it makes it nice and easy to analyze the weight. Okay, we can see that the weight then has a y component and an x component. Now, remember too that we know this angle is the angle that the plane is inclined at, right? It is 20 degrees. So we know all these things about it. Now we have to find out, okay, so what is the force of friction? Now at this point we don't know whether or not it's the maximum force of static friction or not. So we're going to have to assume that it is less than that. In which case, we cannot use the equation mu s times the normal force in order to find the force of friction. We have to find it some other way. So we'll do that by simply summing up the forces in the x direction and seeing what that gets us. So in the x direction, we've got to define our reference frame. I'm going to make down the ramp the positive and up the ramp the negative x directions, simply because I like the idea of the object accelerating in the positive idea better than the negative direction, and yeah, let's just do that. Okay? This means that we're looking at the x component of the weight is in the positive x direction, and the force of friction is in the negative x direction. Knowing that the object has not started sliding yet, that its acceleration is 0, that means the net force on it is 0 as well. So we've got Wx minus the force of static friction. And we'll see that the force of friction in this case is equal to the x component of the weight of the crate. Well, the x component of the weight, you can see theta, we've got that as the opposite again, so this is going to be mg times the sine of theta. We know m, we know g, and we know theta. Putting those values in, we should get a value of about 167.589 blah 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 newtons, or about 168 newtons. Now, this is just the force of friction when we're tilted at a 20-degree angle, but remember that the force of static friction varies depending on the applied force up until you reach some maximum value. And so what we're going to have to do in order to get this file cabinet to slide a little further is tilt it up a little higher. And we're going to tilt it and tilt it and tilt it until the object just starts to slide. Now, we don't know what angle that is at just yet, so let's just call it theta, all right? Now, in this case, we'll want the free body diagram the same, which it's not really going to be any different than it was before. The weight hasn't changed. It's still in the vertical direction, right, straight downwards. The normal force should have lessened a little bit. It is not as much as it was before, and it should be at a greater angle than it was before. Now, this is probably an exaggeration, but we're just going to go with that, okay? Now, we'll also see that the force of friction is going to have increased. And one thing we need to see is now, how does it compare to the x component of the weight? Well, we'll see. Let's put my axis on here first. Okay. I'm still going with the negative x direction being up the incline and the positive x down. Y will be roughly conventional. We'll still have these components of the weight. That's the weight's y component and the weight's x component. This angle now is a mystery to us, and we're trying to find out what that is. So what we're going to see, and we'll see that my free body diagram is not quite drawn to scale as it should be, but what we're going to see is, in order for it to just start to slide, for it to just start to accelerate, there is when the force of friction is equal to the x component of the weight, and then there is that moment just after. And really it only has to be just after, and in fact it only has to be a negligible amount after that. So we can really consider it when the force of static friction is equal to Wx, because the amount that it has to be greater than that is actually negligible. So when we look at what's going on in the x direction, okay. So we'll start off with the same equation that we had before. We'll say the sum of the forces might as well be 0. But there's something different about this now, and that is that the force of friction is now the maximum force of static friction. Okay, so we can put this in. All right, so we've got Wx minus mu s times the normal force. And in this case, we will have to know what the normal force is. So we'll have to go to our y direction and find out from there. So in the y direction, the sum of the forces has the normal force in the positive y direction and the y component of the weight in the negative y direction. Once again, the object is not accelerating in this direction at all, so the sum of the forces in that direction has to be 0. So the normal force is equal to the y component of the weight of the object. So we can take this value, which we can find, knowing the mass of the object and the angle that it's at. We can put that into here to find the angle. So at this point now, we've got 0 equals Wx minus mu s times Wy. So let's start replacing this with what we know. And what we know, well, let me rewrite that really quickly. So we've got 0 equals wx minus mu s wy. So what we're going to do, let's just see, because we're looking for the angle here. So I'm going to go 0 is equal to mg sine of theta minus mu s mg cosine of theta. Now we should see something pretty interesting right away. 0, m and m. What happens to the masses? Mathematically speaking, they cancel. What does this mean in the physics world? In the physical world, this means that the mass doesn't matter. You could have a 50 kilogram cabinet, you could have a 5 gram cabinet, and they'll both have to be tilted to the same angle in order to start moving. The mass doesn't matter. We'll see too, g is going to cancel from our calculations as well. And so if you took this dump truck to the moon, you'd be amazing. But if you did that, you would tilt it to the same exact angle in order to get this file cabinet to start to accelerate. So let's see where we're at. We've got 0 equals the sine of theta minus mu s times the cosine of theta. And, well, we're trying to solve this for theta. So I'm going to add the mu s cosine of theta to both sides. Wow, let's try that one again. So mu s cosine of theta is equal to sine of theta. Divide both sides by cosine of theta, and we'll see that mu s is equal to, well, sine of theta divided by the cosine of theta is the tangent of theta. So when the tangent of theta, whatever angle we're tilting it to, is equal to the coefficient of friction between steel and steel in this case, which is 0.7, our object, whatever mass that object is going to start to slide. Fun.